Just do the video of it.
Yeah, I'll do a quick little brief overview.
Okay, I'm ready.
So pretty much, we're living in the age of technological miniaturization. So our computers and phones and everything's getting smaller. And the same thing is being applied to the satellite and suborbital testing market, which means that our satellites are getting smaller and the payloads that we're trying to carry into space are also getting smaller. And at the same time, we're having a massive increase in the interest in space exploration, which with all these billionaires and private space companies who are trying to build their own reusable launch systems to cut the cost curve of accessing space. But the problem is that all this reusable technology that's being developed is only being applied to the very large orbital rocket boosters. So my idea is, what if we could take this reusable technology and apply it to some of these smaller launch vehicles, which are going to be in higher demand in the near future? So what I did was I worked towards developing a launch vehicle with autonomous landing capabilities, which is one of the primary aspects of full reusability in a rocket. So, plug into my ground control software here so you can see some of the data that comes off this rocket. So this is the rocket right here that I've developed, and if you look closely at this system right here, you can see how the thrust of the rocket changes in relation to the angle of the rocket. And in our flight control software here, you can see all this data updating in real time. So I move the rocket off the front, you can see it move here, and some other propulsion system status stuff there. So one thing that I'd like to note is that all of the hardware, software, electronics, ground station software, simulations, that was all built from the ground up by me, so I could get the most efficient system possible. So in order to propulsively land, we have to be able to stabilize our vehicle on the way down. So this system right here is what stabilizes the rocket as it comes down. And this setup right here is really interesting because it's the first time anyone has ever developed a throttleable solid rocket propulsion system. So here we have pitch control, yaw control, roll control, as well as throttle control. So throttle control is achieved by vectoring two motors towards each other and the other two motors towards each other. So what this allows me to do is throttle the system down to about 77% of the total thrust, which has really been the part that has been limiting everyone else from developing a system like this. So, to control all my thrust vector here, I built a flight computer from the ground up. And this contains all the necessary processing equipment, power supplies, sensor hardware, things like that in order to control this rocket. So in the flight computer that I developed, there's an inertial measurement unit. And that calculates the orientation and measures the acceleration, gyroscopic motion, and magnetometer readings in all three axes of the rocket. And that's sent through a magnetic sensor fusion algorithm, which determines my pitch, yaw, and roll values of the vehicle. I then use a proportional integral derivative control algorithm to stabilize my vehicle. And if you know anything about PID, you know that you have to find the optimal coefficients, the optimal gains, in order to program your system. So I developed a mathematical model of my system in Simulink and MATLAB. I then used a transfer function-based proportional integral derivative optimization algorithm in order to determine those optimal coefficients. I then tested those stabilization coefficients over the course of 8 different hopper, hold down, and drop tests. So I'll cut through some of the earlier testing because it's a little boring and get to the actual landing attempts. So in these landing attempts, for most of them, or for all of them actually, the PID coefficients weren't optimal, meaning that it was overshooting the target a little bit. Here, the rocket also burned through all of its propellant before being able to reach the ground. So here, it loses fuel about 1.5 meters above ground, about 1.4 meters. And in some of the later landing attempts, the stabilization software worked very well, but near the end, the proportional coefficient cut out, so it didn't have enough control authority over the vehicle. The second problem in this test right here was that the motors did not cut out soon enough, meaning that after the vehicle touched down, the motors were still burning, which pushed it back up into the air. So I haven't been able to achieve a full propulsive landing yet, but I pretty firmly believe over the next 3 to 5 landing attempts, I'll be able to achieve a propulsive landing. And going forward from there, I'll be working on some software that cuts out horizontal translations due to wind, things like that. And then eventually working on bleeding off energy by using aerodynamic forces on the vehicle to slow it down further before you're using the propulsion system. to land.
That's great. Thank you.
So I'm super excited to see you at forward.
Thank you. Thank you. And I forgot, you said, where are you from?
Portland, Oregon.
Portland, Oregon.
Yeah.
Awesome. Awesome. And very glad you made it into the exhibit, and fascinating.
Thank you so much. Thank you.
You probably want to meet
Elon Musk?
Elon Musk, yes.
He
yes.
is pretty much my biggest inspiration out there.
Yeah.
So one day I think that'd be super awesome.
That'll be. I'm sure you're going to meet him. I'm sure
Thank
you
you.
will. Okay.
Thank you.
Thank you.